big bends start with serious force, and the UKB Wing Bend Plus system delivers just that. This isn't your average press brake setup. With force capacities ranging from 500 to 2,500 kilonewtons per meter, these tools handle sheet thicknesses up to 12 millimeters. That's raw bending power, designed for high-precision forming across a wide variety of metals. The machines are equipped with hydraulic drives that ensure consistent pressure across the entire bending length, minimizing flex and distortion. Each die is engineered to match specific strength and thickness demands. The Wing Bend Plus 62.120 handles lighter sheets at 1.2 millimeters thick, while the 29.850 takes on the heavy-duty stuff, up to 12 millimeters. The variety of dimensions and tonnages available makes this system adaptable to multiple industrial needs. Tool height and angle are optimized for minimal springback, especially when working with high-strength steels. You can see the tool sets locking in place, ready to mold steel into exact forms. The press descends with precision, applying massive pressure evenly across the sheet. What happens next is controlled deformation, metal folding like it's meant to, without fractures or misalignment. Whether it's 50 millimeters or 500 millimeters dies, each configuration is fine-tuned for accurate, repeatable results. There's something undeniably satisfying about seeing thick steel yield to force so precisely. Crowning systems are also integrated to compensate for deflection, especially under high-tonnage loads. The system's ability to switch between profiles quickly boosts productivity. These tools don't just bend, they simplify complex geometry at speed. Watching it in action, you know this is built for real-world manufacturing pressure. With CNC control over the back gauge and punch travel, setup time between jobs is significantly reduced. Bending large steel parts isn't just about force, it's about control, speed, and consistency. And that's exactly what this system proves in every stroke. This is what brute strength and fine control look like in one frame. The Roundo R13S profile bending machine rolls a massive HEA 650 beam the hard way, on edge. The process starts with hydraulic clamping, locking the profile in place before the powerful rollers engage. Watch how the beam curves steadily under pressure. No sudden jerks, just controlled deformation across its length. The new WCNC4 system calculates each move, adjusting in real time for precise, multi-radius shapes. Rolling a profile of this size isn't just technical, it's a display of confidence in engineering. You can feel the tension, the weight, the exactness. And when the bend holds, it's strangely satisfying to see it all work flawlessly. No welding, no weaving, just one stretch and the metal becomes mesh. A solid metal sheet is slit with staggered cuts, then stretched in one motion. Those cuts expand into a continuous mesh, no welding, no joints. Openings can range from 125 microns to 400 millimeters. It's efficient and strong, using less material without losing integrity. Seeing a flat sheet turn into mesh like that just hits different. This is how welded steel grating is made, used for industrial floors, walkways, and stair treads that need strength and durability. It begins with massive steel coils feeding into slitting machines. Each coil is sliced into narrow strips, then shaped for load-bearing strength. These strips are aligned, crossbars added, and everything is locked together by automated welding. The glow of red-hot edges, the snap of sparks. This is raw steel turning into structured platforms. Cut to size, welded, and trimmed with grinding tools, each panel becomes precise. There's something addictive about watching metal come alive like this. It's loud, it's hot, and every second of it screams pure manufacturing power. Here's how round steel bars are curved into perfect spiral shapes using the Nargisa MC400. This machine runs a 3-roll drive system, ideal for hollow tubes and solid profiles alike. The bar is fed between 3 steel rollers. As the top roll descends and the lower ones rotate, the material bends gradually into a tight spiral. The rollers have smooth surfaces to prevent marking the tube, and their independent adjustment allows for tighter curves with minimal waste. A reinforced welded steel frame gives the machine serious durability, with 130 mm roller diameter and hardened 40 mm shafts. It handles up to 63.5 mm round tubes without flexing. Side guide rollers correct alignment throughout the bend. What looks like a slow spin is actually controlled force and perfect geometry at work. When the steel curls just right into a clean spiral, it's hard not to appreciate the elegance behind such raw force. Strong, precise, and endlessly repeatable. This is no ordinary turning center. The SMX 2100 Street is a super multitasking machine built to cut, mill, and drill complex parts in one setup. With a maximum turning diameter of 600 mm and a length capacity of 1040 mm, it handles large components with ease. The dual 8-inch spindles rotated up to 5,000 RPM, each powered by a 22 kilowatts motor. The milling spindle adds even more versatility, hitting speeds of 12,000 to 20,000 RPM to machine small features with high precision. X, Y, and Z axes offer long travel distances and high-speed movement, up to 48 meters per minute. Tool changes are quick and accessible, thanks to a front-mounted magazine that holds up to 120 tools. CAPT OC6 holders ensure rigidity during heavy cuts. A servo-driven lower turret enables simultaneous machining with up to 12 rotary tools. Watching it all work in sync is intense. The turret shifts, spindles spin, tools fly in and out. Everything is coordinated through a FANUC 31 IB Plus system with touchscreen control. It's not just about automation. This is full-spectrum precision manufacturing. Seeing a raw bar stock transformed in one cycle like this, that's pure machining power on display. It begins with an aluminum mold, where hot wax is injected to form detailed patterns. These wax pieces are welded into a tree-like cluster and repeatedly dipped in ceramic slurry. After each dip, drying time builds up a thick shell strong enough to hold molten metal. Once dried, the entire shell is placed in a high-pressure furnace. The wax melts out, leaving a ceramic cavity. Shells are then fired at over 800 degrees Celsius before molten steel is poured in. Every cavity fills with precision. After cooling, the ceramic is broken off using vibration. Circular saws remove each casting from the cluster. Depending on the application, parts are then heat-treated, machined, or chemically finished. There's something captivating about watching temporary wax become complex metal. This lost wax casting process combines ancient technique with modern precision. An oxygen lance cuts through concrete, steel, even stone, with nothing but heat and pressure. It starts with ignition from an external flame. As oxygen flows through the lance, the metal core reacts, generating extreme temperatures. That intense jet melts and blasts through material like it's butter, watching it pierce solid steel in seconds. Brutal, loud, and incredibly effective. This is raw cutting power, no compromise. This is how forged crankshafts are made. Massive components built to survive the heart of combustion engines. The process begins with a steel billet, superheated until it glows orange, reaching the plastic state needed for deformation. It's loaded into a forging press where every strike delivers thousands of tons of pressure. With each blow, the billet reshapes, slowly taking the form of a crankshaft. Operators reposition it precisely between stages, making sure alignment stays true. Dies are engineered to form complex contours like crank webs, fillets, and counterweights. The metal doesn't cut, it flows. It's compressed so tightly that grain structures follow the geometry of the crank, boosting strength exactly where it's needed. This grain flow is one reason forged cranks outperform cast ones. Each step is measured, monitored, and timed. There's zero room for guesswork. Even the heat radiating off the part tells trained eyes if something's off. The press operates with precise timing to avoid overworking the material. Once shaped, the flashing, the thin excess material, is trimmed clean using a separate die. After forging, the part undergoes heat treatment to balance hardness and toughness. Each crankshaft must survive high RPM, vibration, and combustion shock. It's one of the most critical parts of any engine. Watching that transformation under fire and force, it's more than manufacturing. It's controlled aggression, made into metal. This old horizontal boring mill gets a serious upgrade. The headstock is replaced, bringing modern spindle speeds and power. Now it can handle internal coolant tools with ease. Control systems are updated, guideways rebuilt. Watching this retrofit come alive is like giving old iron a new brain and a new heart. Keeping a 16.5 megawatt generator in top condition takes more than just routine checks. It's a full-scale teardown and rebuild. The process begins with disconnecting and pulling out the rotor, a massive steel core that spins at high speeds to generate electricity. Once removed, the rotor and stator are thoroughly cleaned. Decades of heat and dust leave their mark, and every surface needs attention. Insulation and winding integrity are checked. Technicians assess remaining life by examining wear, hotspots, and material degradation. Bearings are removed and inspected under strict tolerances. Any play or damage could mean catastrophic failure. Wedge tightness is verified, ensuring coils stay secure under load. A bump test checks the end winding stability of the stator, identifying looseness or resonance issues. After inspection, both rotor and stator are revarnished with insulating resin. This helps restore dielectric strength and protects against moisture and vibration. Technicians spray insulating varnish manually. Some areas are treated with a protective coating to prevent corrosion. Electrical tests are repeated to verify insulation effectiveness. Final visual checks ensure no contamination or damage was introduced during reassembly. Everything is rebuilt with precision and documented thoroughly. It's not glamorous, but watching a power plant breathe again after deep maintenance hits different. Each bolt torqued, each bearing checked. It's a reminder that reliability isn't automatic. It's earned through engineering discipline. Before a single train speeds down the track, every rail must be shaped, straightened, and tested with absolute precision. This is how high-speed rails are made at Boeing. Raw steel exits the furnace glowing at 1,250 degrees Celsius, just the beginning of an intense journey through the Boeing rail mill. A high-pressure descaler blasts away surface scale before the billet meets its first shaping stage. In the breakdown mill, powerful reversing stands reduce and elongate the billet. After multiple passes, each piece is turned and aligned by tilters and sintering devices, setting up perfect conditions for the next roll. Then comes the CCS stand group. These high-rigidity stands define the rail's profile with extreme precision. The process isn't just about shape, it's about controlling grain flow, mechanical strength, and microstructure. At rolling speeds up to 8 meters per second, everything must work flawlessly. What's truly impressive is the balance between brute mechanical force and surgical level detail. One misstep, and tolerances could fail. But here, every pass is monitored, adjusted, and verified. After rolling, each rail gets a unique stamp for traceability. It's then slowly cooled on a walking beam bed to around 60 degrees Celsius. Essential for stress relief and shape retention. Straightening follows. Horizontal and vertical machines apply individual forces to perfect the rail's alignment. A 90-degree turn aligns the rail for vertical correction. Final tests check internal and external flaws. Only flawless rails are cut to length and loaded for transport. Behind each section of track lies a precision-driven process, quiet, relentless, and vital to the future of rail travel. Watch a 2-ton forged steel block take shape into the housing of a Boeing 777 landing gear. The process starts with CAD preparation and TIBA software, where engineers refine the 3D model and define machining strategies. Digital work planning selects the best machine and tools using a digital twin. The system simulates the full workflow, checking for collisions, optimizing toolpaths, and ensuring safe transitions. Every cutter, from round insert to ball-end mill, is chosen from Tebis's tool library and applied with precision. Roughing removes bulk material fast, carving deep pockets with short, rigid tools, watching that solid block shed steel in controlled layers. It's just impressive. Toolpath calculations are stored and organized in a digital process plan, detailing each machining step. Engineers rely on this roadmap to coordinate tool changes and cutting operations. During machining, intermediate measurements are taken to verify progress and tolerances. If necessary, minor path corrections are simulated before real cuts continue. Measurement and distance analysis ensure exact geometry, and simulation results guide every move. Re-roughing focuses on remaining stock, tracked digitally for maximum material efficiency. A new machine is selected for finishing. High Precision 3 plus 2-axis milling. This stage handles intricate contours, especially around the hydraulic connection points and mounting surfaces. Some cavities are approached from tilted angles, using multi-axis movements to access complex zones. This isn't just code and metal. It's virtual planning turned real. Toolpaths aren't just numbers. They guide the creation of components that carry lives through the sky. When aerospace quality depends on microns, there's no room for guesswork. Just digital precision, end to end.